Well, welcome back to Chapter 3. Last time we worked in finding areas in between two z-values using the standard normal table. So I'm going to pull up the standard normal table, and we're going to look at the values, the smallest z-values you can get from the table, negative 3.9. Now with that z-value, it tells us the probability is 0.0002. So if we have any number smaller than negative 3.49, what we're going to write is this. We're going to say that the probability that z is less than, and let's say it was 3.5 or 3.6 or negative 3.5 or negative 3.6 or something to that effect. We're going to say then that that probability is less than 0.0002 because that's the best information that we know. We never say that it's 0. We just say that it is less than the last probability that we see on our chart. And we saw on our chart, again, we saw that the smallest number we have is negative 3.49. So any number smaller than that, we're just going to say that the probability is less than this number that we see right here, 0.002. Now, if we're talking about the probability less than 3.49, we would use then this number, 0.9998. So if we have any number greater than 3.49, we would say, again, the same thing that we did for less than negative 3.49. We'd say that that probability is less than 0.002. Now, when we say the probability that z is less than positive 3.5, and so let's say that we have a bigger number than the chart gives us, then we'd say that that's the probability that is greater than 0.9998. Because again, on the table we see that. So you can see from the chart that any number greater than 3.49 we don't have information for. So that's why we say that the probability that any number greater than 3.49, like 3.5 or 4.2, we would just say that the probability that z is less than that is got to be greater than 0.9998. So please make sure that you look on slide 44 and look at these conventions and make sure that you follow them. Now in Minitab, they'll have 0.0000. You just write that as 0.001. And if they have something that like it's close to 1, just write that the area is greater than 0.9999. And this is because the normal curve extends indefinitely in both directions. Now remember that it looks like it's going to touch that z-axis, but it never really does. So there really is no z value for which the area to the left is going to be exactly 0 or exactly 1. So that's why we use these conventions. So a quick review of the standard normal curve. We know that the area under the normal curve can be interpreted as as a proportion or a probability. The standard normal curve can be interpreted as a probability density function. We use z to represent a standard normal random variable, so it has probabilities such as the ones that you see on this slide. And areas underneath the curve of general normal probability distributions can be related to the areas under the curve of the standard normal probability distribution via what we're going to learn now called the z-score. We're going to learn that we can standardize any normal probability distribution and standardize it to this standard normal distributions, and we'll be able to use the table that we used, and we'll be able to interpret proportions or probabilities. So we'll be able to use these standard normal probabilities for any normal distribution once we standardize. Now the standard normal distribution, remember, has a mean of 0 and a standard deviation of 1. So basically we're just looking at how many standard deviations we are away from the mean whenever we look at the standard normal distribution. Well, we've got this number, this z-score, this calculation that you see right here. Z equals x minus mu over sigma. That is a way to standardize any normal distribution to the standard normal. That means that we're finding out that z-score is how many standard deviations that the x value is in its distribution. So again, the z-score is how many standard deviations that variable value x is in its distribution, where it's going to have a mean of mu and a standard deviation of sigma. When we do this z-score, we now have standardized the variable, and now we can say, hey, that x value is 1.3 standard deviations away, and then we can calculate proportions and probabilities using the standard normal table, because we're seeing exactly how many standard deviations it's away from the mean. So this is what I was saying. The standardized score is how many standard deviations a particular data value is in the random variables distribution. So let's look at this example. The mean of these Iowa test scores is 6.84 with a standard deviation of 1.55. So 8.39 is one standard deviation away, 9.94 is two standard deviations, 11.49 is three. But again, I could ask the question, what's the probability that someone would score less than 7.0? How would I handle that problem? That's when we're going to take that score of 7 and see how many standard deviations it is away from the mean and use our standard normal table to help us. So we're going to find out how many standard deviations 7 is away from the mean. So we'd use our z-score calculation. So we'd say 7 minus 6.84 divided by 1.55, and that's 0.103. But our z table only goes to 2 decimal places, so we'll use regular rounding rules to round that number to the nearest hundredths place. And remember how that goes. If it's 4 or less, we're not going to round up. If it's 5 or more, we would round up. Well, that number's 3, so that's less than 5. And so we wouldn't round up, so we're going to keep it 0.10. So now we're ready to use our table to find what's the probability that the z-score, the number of standard deviations away, being 0.10, what's the probability that of any z of that value or less? So we go into our tables, we look up 0.103, and go over to 3, and we find our answer. So the probability that z is less than 0.10 is 0.4602. So in that Iowa example, I can now take any normal distribution as long as I know the mean and standard deviation, and I have a variable value. I can now find in between values. So now in this particular example, let's say that I want to find out what's the probability that someone scores between a 5.8 and a 7.1. Well, now I'm going to do the in-between. I'm going to first find the z-value of 5.8, and then the z-value of 7.1, and then find the in-between. Now remember how we find a z-score. It's z equals the x value that you're looking for minus the mean of the distribution divided by the standard deviation. So I'm going to change these x values into z's. And here they are. Now when I changed 5.8, it became negative 0.671 standard deviations, so the normal rounding rule would make it negative 0.67. When I do the right endpoint, I have 0.168, so that would round it up to 0.17. Therefore, I'm going to find the area of the z less than 0.17 and subtract it from the area less than negative 0.67, as we learned in the last series on our lecture on Chapter 3. So I look at the value of 0.1. I want to look for the probability that z is less than 0.17. When I look on the chart, I look for 0.1, well, 0.1, and then go to the 7 columns. I see the 0.5676. Then for negative 0.67, I look at negative 0.6, go down to the 7 column, and get 0.2514. Now I'm ready to subtract those two numbers, 4, and I now have the probability of z being in between those two standard deviations. So I get 0.3162. That concludes this segment of Chapter 3.